Welcome back. Before we get into the subject of what is known as word problems, and before we get too far into analyzing more complicated algebraic structures such as polynomials, we are going to spend a moment on the subject of equation balancing with arbitrary variables. Earlier in this class, we have learned about the subject of how we solve multi-step LEOVs. And what we saw was that regardless of the type of multi-step LEOV equation that you might be thrown in the textbook, what you're always going to do is you're always going to take a multi-step LEOV, you're going to turn it into a two-step LEOV. Then from a two-step LEOV, you obtain a one-step LEOV. And from a one-step, you have a solution. So this was the general problem-solving strategy when you're just given a single variable and a problem statement such as x plus 7 is equal to 10. You're going to go through the same steps every single time. But here's the deal, guys. What if I told you that if you mastered this process of reducing equations from multi-step LEOV to a two-step to a one-step and finally obtaining a solution, if you truly were able to master utilizing the multiplicative and additive inverse laws, the identity laws, et cetera, then basically you have what it takes to solve a formula that has a bunch of different variables. In fact, not just a bunch of different variables, an arbitrary amount of variables. What does the word arbitrary mean? Arbitrary means that we get to decide based on the circumstances how many variables we would like to play with, and then we could create an equation that we would want to, for whatever reason, solve. And so basically the multi-step LEOV problem-solving strategy sets the foundation for solving equations with arbitrary variable. In our discussion of LEOVs, we saw that we could represent a one-step LEOV as x plus a is equal to b. And we called a constant, b a constant, and we referred to x as our variable. But truly, what is the difference between, say, this particular equation and being given a problem statement such as solve for x and perhaps an equation such as z plus L is equal to m and being given the task solve for z? In the second equation, z plus L is equal to m, we're not necessarily guaranteed that z, L, or m are constants. And in fact, the assumption would be that each one of these values is likely a variable, meaning that depending on the circumstances, they could change. However, regardless of what the specific value of L and M happen to be, it's irrelevant, right? Just like these constants for the one-step LEOV problem statements were irrelevant. We don't need to know what A is. We don't need to know what B is. And we certainly don't know by definition what the variable X is. It's our unknown number by definition. It's irrelevant because we know that to solve a one-step LEOV, regardless of the value A, whatever that value happens to be, we're going to use the additive inverse on both sides of our equation. And then what needs to happen is we need to see that A is lined up with a negative inverse of A. And if that's the case, then our A's on the left-hand side will add to 0. And then on our right-hand side, you're just going to get B minus A. So at the end of the day, because X plus nothing is just X, by the identity law, you have X is equal to B minus A. And that would be our solution. So the long and the short of it is, if you're just given an equation, Z plus L is equal to M, solve for Z, this is going to be the same thing. When we say the word solve for Z, it means we need to do a rearrangement of this formula such that we get Z on one side and all of our other variables on the other side, just as we did before. And so to that end, I see that L is being added with Z. If I want to move L from the left side of my equation to the right, or vice versa, because it's being added with another variable, we need to use the additive inverse. So that's all you have to check, guys. If a number is being added with something else, you should know you need to use the additive inverse to move it from one side to the other. So we will just use a negative L. We'll add negative L to both sides of our equation. L plus a negative L by the inverse law, that's going to be 0. We'll have M plus a negative L, which is the same thing as M minus L. Z plus 0 is just Z by the identity law. And finally, we get our solution. And look, the thing is that it really doesn't matter if L was a positive number or a negative number. We're going to go through the same steps regardless of whether the value is positive or negative. Let's look at what that looks like. So suppose instead I had Z minus L is equal to M. At the end of the day, in order to move L from the left to the right side of my equal sign, all we have to do is recognize that subtraction is the same thing as addition of a negative number. And so because this negative L term is being added to Z, just like before, we're just going to need to use the additive inverse of a negative L, which is a positive L in this instance. And we'll add a positive L to both sides of our equation. Negative L plus positive L is going to be 0 by the inverse law. You have Z plus L, which just gives you Z. And we have our solution. Okay. Suppose now you have two numbers that are multiplied with each other. Suppose you have an A times X is equal to B. We saw that this was also a one-step LEOV problem statement. And if we wanted to solve for X, we would just take the multiplicative inverse of A on both sides, and we would be able to obtain 1 times X is equal to B over A, and then 1 times anything is just that something, so we get X is equal to B over A. Okay, so this was our one-step LEOV problem statement solving strategy, right? But now, suppose we have an equation, and instead of this constant A, this constant B, and X, you have something like, I don't know, K times T is equal to V. I don't know what K is. You don't know what K is. I don't know what T is. You don't know what T is. I don't know what V is. You don't know what V is. But if the problem said solve for K, or actually we'll make it easier, solve for T, the problem solving steps of what we're going to do to get T by itself on the left side of our equal sign are not that different from the problem solving steps that we use to get X by itself. And in fact, they're not different at all. The only thing that's different is that you have different letters. And so in this instance, we're going to use the multiplicative inverse on both sides of our equal sign. And we want to multiply by the value that's in front of T. We're not going to attack T itself because we want T to still remain after all is said and done. And so instead we look to the left of T, or to the right of T, to the numbers that are next to T, basically. And we see that there exists this variable K. So the strategy is we want to see what relationship K has in the equation. And in this instance, K is being multiplied by T, just like the A was multiplied by X. And what that tells us is, in order to remove this value that's in front of T, we don't know what it is. We don't know what the value is. It could be like 10 million. It could be 2. It could be 50. It doesn't matter. To remove this value that's in front of my T, all we got to do is do the multiplicative inverse, because the multiplicative inverse removes a number that is multiplied with another term. So if we use the multiplicative inverse, in this case 1 over K, the k's will cancel out because you'll have k over k. And on the other side of your equal sign, you're going to have v times 1, which just gives you v all over k. K divided by itself is just 1, so you'll have 1 times t is equal to v over k. And then this gives you t is equal to v over k, and that's your answer. Done. You're done. Now, the tricky part of these problems with arbitrary variables is just remembering that you can also do rearrangement. And so suppose you had an equation like t times, let's say it's a negative k, or we'll do negative t times k is equal to v. And it says solve for t. Okay. Here again, just like before, we want to finesse this equation to get t on one side and everything else on the other side. The only real difference, however, is that when you look to the previous equation, on the one hand, we were multiplying 1 over k on the left-hand side of our variables. Do you guys see that? We've got 1 over k times k, because k itself was parked to the left of our t. So students would get confused here because they see k is on the right-hand side, and of course they might make a big stink about this. But truthfully, it doesn't matter if k was on the left or on the right, or if you multiply on the left or you multiply on the right with your inverses for that matter. All that matters is that your inverse is multiplied somewhere, and that generally speaking, you want your variables that are being multiplied by your inverses to line up so that you can do a accounting step for the numbers canceling out. Now, what that means to you is that if I wanted to get t by itself, I have a number of options. Option 1 would be we use the commutative law, and I simply switch my terms. So this would be my option 1. Like, if you're really bothered and you really psychologically need your equations to line up with something that looks similar to a problem statement you've seen, then go ahead and do this. So option 1, we use the commutative law to switch the order of k and t, and we could do that so long as we remember these numbers are multiplied with each other. It's not negative k plus t. T isn't being added with k. It's negative k times t or negative t times k, and you could just switch the order of those terms. Now, the reason why we would want to do that is that, okay, if we did this, we could right off the bat just copy the steps we had before, which would be multiplying by the multiplicative inverse of, in this instance, a negative k, because we have a negative k that is a leading term. And when we do that, we get a negative, and a negative is a positive. You'll have k over k, t. And on the right hand side, you've got 1 over negative k times a positive v. Well, a negative and a positive is a negative. V times 1 is v all over k. Okay, take a deep breath. K divided by k just gives you 1, so you'll have 1 times t is equal to negative v over k. And you have your answer. T is equal to negative v over k. Voila. All right, but remember that's option number 1. Option number 2 would be that you did not move your k because you're not frightened by this idea that we could have just multiplied 1 over k. And in fact, we might as well just multiply 1 over a negative k on both sides of our equal sign. And in this instance, we'll multiply on the right because why not? So I'm going to multiply on the right-hand side with this negative 1 over k. And we've got a negative term, this negative tk times negative 1 over k. So negative and negative is a positive. And you will have t, k times 1 is k, v times 1 is v all over negative k. Your k terms basically cancel out just like they did before. You've got t times 1, because anything divided by itself is just 1, is equal to negative v over k. T times 1 is just t, so you get t is equal to negative v over k, and that's your answer. Okay. So the multiplicative and additive inverse are the two basic rules that you have to have a command of. But then, of course, you can extend this. You can start, throwing in distribution law problem steps, or even fractions for that matter. So you could have something like this. Could have the following problem. Okay, so this problem, unlike the others, cannot be solved in a single step. And in fact, you've got, in this instance, 5 variables that are all different from each other. We don't know what A is. We don't know what V is. We don't know what L, B, or P is. We don't need to. All we're going to do is we're going to use the multiplicative and additive inverse laws to finesse this equation to get A on one side and everything else on the other side. And we're going to do that one step at a time. So I'll tell students, do this one step at a time and be very, very careful with your work. Otherwise, you're just going to make a mistake. So the thing is, we really don't necessarily need to focus on this A term, this A over B term, this first fraction. And instead, uh, we should focus on the fact that there's an addition operation with this V over P term. So if we did that, we could basically imagine this problem being a more sophisticated version of an additive inverse one-step problem statement, where all we need to do is move that move the V over P term rather from the left side to the right side of our equation using a additive inverse. So let's go ahead and do that. All we're gonna do is we're gonna add a negative V over P to both sides of our equation. When we do that, we got V over P plus negative V over P. That's gonna give you 0. A over B plus 0 just gives you A over B. And you get L is L minus V over P is equal to A over B. All right. So now the issue is, what can we do to get A by itself? There's naturally this fraction, right? And the trick of this problem statement, and usually the trick of being able to manipulate fractions in general, is just remembering that anytime you have a composite fraction, an A over B, this is the same thing as A times 1 over B. And so at this point where you've got this A over B, if I wanted to get A by itself, go ahead and split up the fraction. You just say, okay, well, this is the same thing as A times 1 over B. And the worst thing that's going to happen is that this is just a meaningless step and like it's more work. But the best thing that'll happen is when you start breaking up these fractions, you actually get a hint as to what you need to do next. And the hint here is that, oh, hey, remember how division is just the same as multiplication with the inverse? Okay, so because that's the case, you have this 1 over b term. It's being multiplied by a. And remember, anything that's being multiplied by a number, if you want to get rid of it, you got to use that multiplicative inverse. And so that's what we're going to do right now. The multiplicative inverse of 1 over b, or the reciprocal of b, is going to, or 1 over b, is just going to be b over 1. And so we have to be very, very careful about what we do here. When we multiply by b over 1, we got to multiply the entire second equation on the right side of the equal sign by b over 1, or just b. Now what's going to happen is b times 1 gives you b, b times 1 gives you b, b divided by b gives you 1. And then you have all of this equal to L minus V over P times B, basically. So my A is equal to L minus V over P times B. That's all we do. Okay. Now for a distribution problem, suppose you have a times t minus wz, and this is equal to m plus g. And we want to solve for w. Okay, so there are a number of different ways that you can approach this type of problem. On the one hand, you can treat this setup such as it exists, where you pretend this t minus wz is just some unknown value multiplied with a. And if you did that, considering that you want to get w by itself, because that's the goal, we're trying to solve for w, we need to remove the a term. And because a is being multiplied with this x, you would use the multiplicative inverse of a on both sides. And you have to do that very, very carefully, just like the previous problem. You can't do this all willy-nilly. I can't multiply the 1 over a just by the m term. I can't multiply it by the g term. I have to multiply it by both those terms added together, just like I've done here. So don't go super fast, otherwise you'll mess that step up. And we get x by itself is equal to 1 over a m plus g. But now at this point, we know that x was the same thing as the t minus wz. And so now we can remove the parentheses from around our t minus wz, because at this point, we can start operating on either the wz or the t term. And in fact, maybe I'll go ahead and I'll get rid of t. I'll add a negative t to both sides of my equation. My t's will cancel out. They'll just become 0. And then you have negative wz is equal to negative t plus 1 over a m plus g. And that's like basically what you have there. Now, you can multiply both sides at this point. If you want the w by itself, why don't we multiply by a negative 1 over z? Because we have a negative wz. We got to get rid of that negative symbol at some point. We might as well multiply by a 1 over a negative z. And what we do to one side, we got to do to the other. So go ahead and do that same operation to the other side of your equal sign. And it's going to look rather nasty, but at the end of the day, negative is a positive. W will be by itself because W times 1 is just W. And then on the other side of your equal sign, you've got negative t plus 1 over a times m plus g, all being multiplied by negative 1 over z. And that's your answer. And it's pretty nasty, but it's an answer. Now, note that that was one way we could have walked through the steps in order to obtain what we wanted, which was W by itself. However, note that there are also other ways of doing this. Note that as long as we are using the rules of algebra, we can always obtain the correct answer. So if we backed up for a second and instead we consider this particular equation, a times the quantity t minus wz is equal to m plus g, and say we were solving for w instead, what we could have done is use that distribution law. If we use the distribution law, you got a times t plus a times negative wz is equal to m plus g. Now, while at first this may not seem like the most optimal choice of steps, I'm going to show you that it's just fine. We're just fine. At this point, we will add a negative at to both sides of our equal sign. our A and our T term will cancel out. That'll just add to 0 because we know that that's an additive inverse. It looks nasty, but it's an additive inverse at the end of the day, guys. Okay. 0 plus anything is just that something. So we now have a positive and negative. A negative A WZ is equal to negative AT plus M plus G. So that seemed to me to be a faster way of attacking the problem. Now, I don't know. Maybe you guys would say differently, but I think it's a little bit faster. Now, the thing is that students will get confused because they've got 3 variables all being multiplied together. And, they don't know perhaps what they should multiply as an inverse for this problem statement in order to clear out the Z and the A. And so, but here's the deal, guys, because all of these numbers are being multiplied together with each other. Due to the commutative law, you can switch the order of the terms. And so if you know that you need to isolate Z, if you know that you need to remove the Z and the A, on the one hand, you could write in this step, an extra step, and just, move your terms together. Or alternatively, you just say, I know I need to remove the A and the Z term. I know they're all being multiplied by each other. And in this instance, there's also a negative symbol that I'd like to remove. So what we're going to do is we're going to take a 1 over negative AZ, and we'll multiply that on both sides of the equation. Now, what this is going to do for you is that your Z term and your A term, your negative A term, will divide out to be 1. So we'll have W times 1 is equal to, and this formula is going to look a little bit different, but it's actually the same formula. It's going to look a little different, but it's the same formula. So you get W is equal to negative AT plus M plus G times negative 1 over AZ. And of course, this is going to be the same thing as negative AT plus M plus G. Put a negative sign out in front of it. Have an AZ in the denominator. And that is your answer. This is your solution. That's it. That's all you've got to do. Now for section 2.4, the types of problems that you encounter are usually going to be word problems, but they'll actually give you some sort of a formula that you usually have to manipulate. And so, they might say, solve the formula P is equal to 2L plus 2W 4W. They might give you some formula like this and then say solve for W. Because we have been trying our hand at these much more complicated problems, we're now experts at what we need to do for these much simpler problems. And we know that if we want to solve for W, whether we're solving for an equation, for a term inside of an equation on the right-hand side or the left-hand side, we just know that we need to get all of our terms either collected together on the right-hand side or collected together on the left-hand side, whatever side that happens to be the opposite side from the variable that you're solving for. Okay, so since the variable I'm solving for, W, is on the right side of the equal sign, I'm going to collect all of my terms to the left side of my equal sign. All right, so the first thing you're going to notice here is you've got a 2L that is added to a 2W. You know you're going to need that additive inverse. Go ahead, you're going to use that additive inverse. Go add negative 2L to both sides of your equation. I'm going to add them on the left-hand side. Boom, you get 0 is equal to P plus negative 2L, okay, plus 2W. So you got 2W is equal to negative 2L plus P. You're almost done. Go ahead and use that multiplicative inverse law. Both sides of your equation. You've got W is equal to negative 2L plus P times 1/2, or you can write it negative 2L plus P all over 2 is equal to W. And that is all we have to do. Okay, guys, I will see you in class.